What the heck?
Tagon.
Gus! Gus! Hey, Gussie. Hi. Who's a good boy? What are you doing? What are you doing? Who's a good lad? Very good.
So today we're going to do a little homage to another YouTube channel that I've recently discovered and found that I quite enjoy, and that would be the YouTube channel Michael Penn, who does some very, very good explanations of some very, very wacky calc problems, among many, many other things. I mean, he's a very versatile math YouTuber. It intrigued me, the style of solving a particular type of integral involving the floor function in the power of the function involved, which is quite strange, something I wish I'd thought of. But what I did instead was I took his idea and I sort of ran with it, and I came up with a couple more examples that I think are very, very interesting. And so let's do it now. This is the next episode of
Monday Math Nuggets.
Yeah. Even though there's calculus in it. Because I have wackier calculus for wacky calculus. Let's do it. So to start off this here video, let me just quickly cover the result that Michael Penn was able to derive. So he was able to show that if you start off with this integral here, so the integral from 0 to 1 of -1 to the power of the floor of 1 over x dx, he was able to show that this is precisely 1 minus log 4, or 1 minus 2 times the log of 2. Either way, that's a negative number. It's only slightly negative. It's something like negative, probably like 0.7 or something like that, because this will be like 1.3. So something like negative 0.3 or something like that. And he did it through a substitution and then turning the resulting improper integral into an infinite sum and evaluating the infinite sum instead, which is just a very clever way of going about it. And so I'm going to present a couple equally cool examples, I think, of something similar to this. The first one we're going to do is take a look at, we're going to do -1 to the power of the floor of 1 over x, all divided by x, and we're going to do that from 0 to 1 as well, dx, like so. Right? So this is a slightly different, this is what I meant by running with it, like I'm just taking the similar idea and just applying a different function to it, because I think it's a neat concept, a neat idea. So we're going to do the same substitution that Michael Penn did. He said u equals 1 over x, which tells us that x is equal to 1 over u, which tells us that dx is going to be equal to -1 over u squared du by simply differentiating. And the bounds are going to change as well. If we do this now, if we plug in 0 into here, we get positive infinity because we're approaching 0 from the right. And then we get 1 in the top because 1 divided by 1 is just 1, of course. And now we're going to make our substitutions. So we're going to have -1 to the power of the floor of u, right, because 1 over x is u, and we have 1 over x in the function, right, 1 over x, so we can multiply by u on top, because 1 over x is u, but then dx is -1 over u squared du, so we can put the du there, and the -u squared down there, and then what we're going to do is we're going to cancel the u in the top with one of the u's on the bottom, and then we're going to use this negative to flip the bounds of the integral. So we don't have to worry about things being done oppositely. So as it turns out, the original integral we started with, which was the integral from 0 to 1 of -1 to the power of the floor of 1 over x all over x dx, it's now equal to the integral from 1 to infinity of -1 to the power of the floor of u over u du. So it's sort of like we're now going from, instead of 0 to 1, we're going from 1 to infinity, and we've slightly changed the function. That's really all that's happened here. And we're going to utilize the exact same tactic that Michael did, where he realized that this integral from 1 to infinity is just the same as the integral from 1 to 2, plus the integral from 2 to 3, then 3 to 4, all the way up to infinity, which means we can rewrite this as an infinite sum in that way. So we have this sum from k equals 1 to infinity of the integral from k to k plus 1 of -1 to the power of the floor of u all over u du. Now, the fantastic realization that Michael had in his video was that since this is the floor of u, let's remember what the floor is, it's the greatest integer function, right? So it gives you the biggest integer that's less than or equal to u. So if u is 5, then the floor of u is 5. If u is 5.1, then the floor of u is still 5. But notice that we've broken our integral up into integer interval integrals, parse that one, that go from n integer k to another integer k plus 1, which means every value that u takes between those will have a floor of k. Because every number between k and k plus 1, excluding k plus 1, will have the floor of the lower integer, which means we can just write this floor of u part as k. Right? Because floor of u is going to be whatever value k takes on in each of these intervals from k to k plus 1. And now that power of -1 doesn't depend on u anymore, and so we can factor it out of the integral. And we have the sum from k equals 1 to infinity of -1 to the power of k times the integral from k to k plus 1 of du over u. And of course, this is just the natural logarithm of the absolute value of u, but because this is always over some positive integers or positive numbers, we don't have to do the absolute values, and so what we end up with is the infinite sum from k equals 1 to infinity of -1 to the power of k of the natural logarithm of k plus 1 minus the natural logarithm of k. And what's nice about this is we can use the rules for natural logarithms, right? We can combine these two terms together. Where did my eraser go? I could use that. There it is. We can combine these two things together because the difference in logarithms just means you can divide the inputs, right? So we can write this as the log of k plus 1 divided by k. Now you might think we could write this as log of 1 plus 1 over k. We're not actually going to do that. We're going to leave it as is, and what we're going to do is we're just going to inspect the terms that we get from this just to see how it turns out. So what I'm going to do is I'm going to make this slightly easier to see what it's going to be. I'm going to raise the power of -1 by 1, and then just multiply by -1 on the outside there, so that they cancel each other and I still end up with the same term. So let's write out a few of the terms that we're actually going to see here. So when we plug in k equals 1, for example, we have this, so I'm just going to write this -1 out the front that we're going to have the entire time, like that. We're going to have -1 to the power of 1 plus 1, which is -1 to the power of 2, which is of course just 1, times the logarithm of 2 over 1. So we have log 2 over 1 as the first term. And then we plug in k equals 2, we're going to get -1 to the power of 3, which is -1, times log of 3 over 2. But because it's minus log of 3 over 2, we can bring that negative into the logarithm and use it as a power to reciprocate the input. So instead of having minus log 3 over 2, we're going to have plus log 2 over 3. Remember, reciprocals as inputs in the logarithm give you the negative of the original output. So if you plug in a over b into a logarithm, you're going to get the negative of what you get if you plug in b over a into a logarithm. Then of course we plug in k equals 3, and we get -1 to the power 4, which is again 1, times log of 4 over 3. So we get plus log 4 over 3. And then the same thing is going to happen again, where we're going to get log of 5 over 4, but we're going to have a -1 out the front, so we're going to plug that -1, we're going to bring that -1 into the logarithm and reciprocate, so we're not going to get minus log 5 over 4, we're going to get plus log 4 over 5. And so we're going to end up with a bunch of positive logarithms that have these alternating reciprocal things going on here. So we have 2 over 1, then 2 over 3, then 4 over 3, then 4 over 5, and then we're going to get 6 over 5, then 6 over 7, then 8 over 7, and 8 over 9, and so you're going to get like two of each odd number in the bottom except 1, and 2 of each even number in the top. And because of the way logarithms work, we can rewrite this by combining all of these together as a logarithm of a single infinite product. We're going to get minus the logarithm of 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times 6 over 5 times 6 over 7, etc., etc. And some of you might be astute in two different ways. One, you either know this product or you saw my live stream from not too long ago, from when I got 1,000 subscribers. This is the Wallace product for pi over 2. This product here is equal to pi over 2. It can be derived from the infinite product form of the sine function, which means that this whole answer is minus the logarithm of pi over 2. Or we could bring the negative inside and get an even neater looking answer of the logarithm of 2 divided by pi, which I believe is about negative 0.45, I think. And so that's the final answer. This integral right here is precisely log of 2 divided by pi, which is just a great result. I think that's really, really neat. Very, very cool. And I just wanted to show one more cool example of this tactic of solving strange integrals involving the floor function, because it's very, very cool. I hope that was nice. But we have one more cool example I'd like to show you, and that would be this example right here. We're going to do the integral from 0 to infinity of negative 1 to the floor of x divided by e to the x. Of course, we're going to do the same exact tactic where we break this up into a sum of the integer interval integrals. I love calling it that. Integer interval integrals, integer interval integrals, integer interval integrals, integer interval integrals, integer interval integrals. Cool. And so that's simply going to appear as the sum from k equals 0 this time to infinity of the integral from k to k plus 1 of negative 1 to the power of the floor of x over e to the x dx. But of course we can use the same argument that the floor of x is going to be k no matter what value of x, no matter what the value x takes on between k and k plus 1. So we can factor it out as something that doesn't depend on x. So we have the sum from k equals 0 to infinity of negative 1 to the power of k times the integral from k to k plus 1 of e to the negative x dx, which is quite easy to evaluate because e to the negative x has a very simple antiderivative, and we end up with the sum from k equals 0 to infinity of negative 1 to the power of k times the quantity negative e to the negative quantity k plus 1 plus e to the negative k, right? Just using the fundamental theorem of calculus to solve that problem. I hope that's clear. All we have to do is sort of manipulate this a little bit, and we'll see that the answer comes out quite simply. What I'm going to do is just rewrite these as fractions instead of with negative exponents. So we have the sum from k equals 0 to infinity, negative 1 to the k, times the quantity 1 over e to the k minus 1 over e to the k plus 1. And of course what I'm going to do is I'm going to multiply this by e in the numerator, and then have e to the k plus 1 in the denominator. And now what I have is the sum from k equals 0 to infinity of negative 1 to the power of k times the quantity e minus 1 all over e to the k plus 1. E minus 1 on its own doesn't depend on k because it's a constant, and so I'm going to factor it out and make it 1 minus e so that I get an extra factor of negative 1, and then I have the sum from k equals 0 to infinity of negative 1 to the power of k plus 1 divided by e to the power of k plus 1, which of course can also be written as 1 minus e times the sum from k equals 0 to infinity, or we can write it as actually k equals 1 to infinity of negative 1 over e to the k. So I just increased the index by 1, so I had to decrease k by 1, or I had to plug in k minus 1 where I saw a k. But this is of course just a geometric series, right? Negative 1 over e has an absolute value that's less than 1, and so I can apply, as black pen, red pen would call it, our best friend. And we're going to end up with 1 minus e times negative 1 over e divided by 1 minus negative 1 over e, of course, because that's how that works. The negatives will cancel, and we can multiply the top and bottom by e, and so we'll end up with 1 minus e times negative 1 divided by e plus 1. The negative 1 and the 1 minus e will cancel, and we'll end up with this lovely little result that this integral Bringing it up here, this integral, the integral from 0 to infinity of -1 to the floor of x over e to the x dx, is precisely equal to e minus 1 divided by e plus 1. And I just thought that was a very charming result, and I loved it when I saw it, and I just think it's a neat little thing. Cool number, indeed. I think those are two very neat results that are in the vein of what Michael Penn did in that video. I'll link to the video in the description and earlier on in this video. Thank you very much for watching, and as per usual, I hope that's clear. Bye, Gus. Cutie pie.